November 7, 1941. The Bureau of Ships Building in Washington. A grey afternoon with rain streaking the windows. John Niedermair sat at his drafting table, staring at an impossible problem that had just walked through the door with a British delegation. The Admiralty men had laid it out plainly. Britain needed ships that could cross the Atlantic Ocean in winter storms, carrying 30-ton Churchill tanks, ships that could then beach themselves on French shores and drive those tanks directly onto hostile beaches defended by German artillery. No docks, no cranes, no time to offload using conventional methods. Every naval architect in the room understood what they were asking for. They wanted a ship that violated the fundamental physics of hull design. A ship that needed deep draft for ocean stability but shallow draft for beaching. A ship that was both things simultaneously, which was impossible. What Niedermair didn't know, as he picked up his pencil that November afternoon, was that his answer to this impossible problem would enable every major Allied amphibious operation of the war, that his rough sketch, drawn in the following days, would become the blueprint for more than 1,000 ships, that his innovation would land 150,000 troops on Sicily's beaches, would put Allied forces ashore at Normandy on D-Day, would carry the war island by island across the Pacific to Japan's doorstep. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The ships he was about to design would suffer fewer losses than any vessel of comparable importance in naval history, not because they would avoid combat, but because the solution to the impossible problem would make them nearly impossible to sink. The journey to Niedermair's drafting table had begun 16 months earlier, on the beaches of Dunkirk. Between May 26 and June 4, 1940, over 300,000 British and French troops had been evacuated from that French port. They escaped, but they left behind virtually everything they needed to continue fighting. Hundreds of tanks, thousands of vehicles, artillery pieces, heavy equipment, everything too large to carry onto the fishing boats and pleasure craft that had performed the miraculous rescue. The lesson was brutal and clear. Modern armies needed heavy equipment to fight, tanks, self-propelled artillery, trucks, supplies measured in thousands of tons, but conventional shipping required port facilities, cranes to lift tanks, docks where ships could moor, infrastructure that took months to build and could be destroyed overnight by enemy action. If the Allies were ever going to return to France, if they were going to invade German-held Europe, they needed a way to put armies ashore without ports. They needed ships that could beach themselves and disgorge armoured divisions directly onto hostile shores. The British had attempted a solution. 3 shallow draft tankers from Lake Maracaibo in Venezuela, built to pass over restrictive sandbars, had been requisitioned in 1940 and early 1941. The Bachaquero, Misoa, and Tasajera were sent to Belfast, Northern Ireland, where shipyard workers cut off their bows and installed enormous hinged doors and ramps. The converted tankers could carry 22 25-ton tanks or 18 30-ton tanks, plus 2 landing craft mechanized. Trials in summer 1941 showed they worked, barely. The bluff bows pushed water like bulldozers, making the ships painfully slow. Loading and unloading took forever. The conversions were stopgaps, not solutions. Then the British attempted a purpose-built design. HMS Boxer and her sisters Bruiser and Thruster, ordered in March 1941, were Winston Churchill's vision of an Atlantic tank carrier. Built at Harland and Wolff in Belfast, they could carry 13 Churchill infantry tanks, plus 27 other vehicles, and nearly 200 troops. They could make 18 knots, respectably fast for cargo vessels. But the Boxer-class ships still required long ramps stored behind bow doors because their hulls drew too much water to beach directly. The ramps were unwieldy, difficult to deploy under fire, vulnerable to heavy seas. British naval architects had improved on the converted tankers, but they hadn't solved the fundamental problem. Deep draft for ocean crossing meant the ships couldn't beach. Shallow draft for beaching meant the ships wouldn't survive ocean crossings. The laws of naval architecture didn't allow both. At the Atlantic Conference in Argentia, Newfoundland, in August 1941, President Franklin Roosevelt and Prime Minister Churchill discussed the problem. Both men understood that the Second Front, whenever it came, would require thousands of amphibious vessels. Landing craft for infantry were being developed, but nothing existed to land the armoured divisions that would be essential for success against German defenders. Churchill had been thinking about tank landing vessels since World War I, when he had served as First Lord of the Admiralty. Now, 23 years later, with Britain fighting for survival, he insisted that the problem be solved. The Americans, he argued, with their vast shipbuilding capacity and engineering talent, should take the lead. In November 1941, a small British delegation crossed the Atlantic and met with the United States Navy's Bureau of Ships. The requirements they presented were specific. The vessel had to cross the Atlantic independently. It had to carry a significant number of tanks, preferably 30-ton American Sherman tanks or British Churchills. It had to beach directly, without requiring port facilities or external ramps, and it had to do all this reliably, in seas that could destroy conventional vessels. The meeting took place in a world at war, but before America had officially entered it, Pearl Harbor was 4 weeks away. The U.S. Navy was expanding rapidly, building destroyers and battleships and aircraft carriers. The Bureau of Ships was overwhelmed with work, every drafting table occupied, every engineer working multiple projects. The Admiralty men presented their problem and waited. The American naval architects listened and understood immediately why this was different from anything in their experience. Ships were designed for specific purposes: destroyers for speed, battleships for armored firepower, cargo ships for capacity. You optimized for one thing and accepted compromises in everything else. But a tank landing ship required optimization for contradictory purposes. Ocean-going stability demanded deep draft, 6 to 8 feet at minimum, with rounded hull lines that would rise and fall with swells without excessive rolling. Beach landing required shallow draft, 3 feet or less forward, with flat bottom that would ground gently and remain upright when the tide receded. No ship could do both, or rather, no ship designed using conventional thinking could do both. John Niedermair was not a typical naval architect. Born sometime in the early 1800s, details of his early life remain sparse in historical records. He had risen through the Bureau of Ships by solving problems that stumped his peers. As technical director of preliminary ship design, his job was to take requirements that seemed impossible and find ways to make them work. He understood ship design the way a chess master understands the board. Every decision created consequences. Every advantage required a trade-off. The art was finding the trade-offs you could live with. For 3 days after the meeting with the British delegation, Niedermair thought about the problem. He ignored his other work. He sat at his drafting table with blank paper and a pencil, sketching hull forms and running calculations. His colleagues left him alone. They recognized the signs. When Niedermair went into that state, he was working through something complicated. The answer, when it came, was so simple that Niedermair later couldn't remember the exact moment of realization. It simply appeared, fully formed, as solutions sometimes do when you've been thinking about a problem long enough. You couldn't make a ship that was both shallow draft and deep draft using conventional hull design, but you didn't need to. You needed a ship that could change its draft. A ship that rode deep in the ocean and rode shallow near the beach. Ships already had ballast systems. Tanks that could be flooded with seawater to adjust trim, to compensate for fuel consumption, to maintain stability. But conventional ballast systems were small, measured in hundreds of tons. What Niedermair was imagining was something entirely different. A ballast system so large it would fundamentally alter the ship's draft. A system that would be the central feature of the entire design. The ship would sail across the Atlantic with ballast tanks full, riding low and stable with draft of 14 feet or more. Then, approaching the invasion beach, the crew would pump out the ballast. Thousands of tons of seawater, expelled overboard through high-capacity pumps. The ship would rise in the water like a submarine surfacing. The forward draft would drop to 3 feet 9.5 inches. Shallow enough to drive onto most gently sloping beaches. It was audacious. It was unconventional. It violated no laws of physics, but it challenged every assumption about how ships should be designed. Niedermair had essentially proposed turning the ship into a controlled submarine that could adjust its buoyancy to suit immediate tactical requirements. He began sketching, a hull form with flat bottom instead of the conventional rounded hull. This would allow the ship to ground without rolling over when the tide went out. Twin propellers and rudders, positioned high enough that they wouldn't strike the seafloor during beaching. Bow doors, enormous hinged affairs that would swing open to reveal a ramp. A single tank deck running nearly the full length of the ship, 300 feet of open space where vehicles could park. The sketch was rough, more concept than detailed plan, but it showed everything that mattered: the flat-bottomed hull, the bow doors, the approximate dimensions, most importantly, the notation indicating massive ballast capacity integrated throughout the hull structure. Niedermair submitted his sketch on November 5, 1941. The British delegation reviewed it immediately. They asked questions about structural strength, about seaworthiness, about capacity and speed. Niedermair had answers, supported by rough calculations. The ship would be slow, perhaps 10 knots maximum. It would be ungainly, with the blunt bow common to all beaching craft. But it would work. On November 5, 1941, the Admiralty approved the design. 2 days later, they formally requested that the United States build 200 of these ships for the Royal Navy under Lend-Lease. The vessels would be designated landing ship, tank, or LST. The number 2, in parentheses, LST-2, would distinguish them from the earlier British designs. What happened next would have been impossible in peacetime. The Bureau of Ships immediately began refining Niedermair's concept into detailed working drawings. But they didn't wait for those drawings to be completed. They didn't build a prototype and test it. They didn't conduct the methodical evaluation that normally preceded ship construction. Instead, they started building. The initial specifications called for an LST 280 feet in length. Within weeks, that was changed to 290 feet. Then, in January 1942, to 328 feet. Each change was driven by practical considerations discovered during the design process. A longer hull distributed weight over a greater area, allowing the ship to ride higher in the water when ballasted out for landing. Longer length also permitted wider bow doors, 14 feet instead of 12, which would accommodate almost any Allied vehicle. The beam was set at 50 feet. Draft, when fully ballasted, would be 14 feet. Draft, when pumped out, would be 3 feet 9.5 inches forward. The LST could carry 2,100 short tons of cargo, 20 Sherman tanks on the tank deck, with space on the weather deck above for additional vehicles, or 18 30-ton tanks, or, if needed, hundreds of tons of ammunition, or supplies, or troops. The steel plating varied from 1/4 inch to 3/8 inch on the deck and sides. 1 inch thick plating went under the bow, where the ship would strike the beach. The armor was minimal by warship standards, but sufficient to stop small arms fire and shell fragments. LSTs would rely on speed and surprise and fighter cover for protection, not armor plate. The propulsion system was simple and reliable. 2 General Motors EMD diesel engines, 12 cylinders each, rated at 900 horsepower per engine, at 744 revolutions per minute. Direct drive to twin screws. Maximum speed would be 11.5 knots, though most LSTs made closer to 9 or 10 knots loaded. The slow speed was a compromise Niedermair and the Bureau of Ships accepted because the alternative was worse. More powerful engines meant more fuel, more weight, more complexity. And LSTs needed that weight capacity for cargo, not machinery. The ships would cross oceans slowly. That was acceptable because they would arrive with the tanks and vehicles that would win battles. The ventilation system was crucial. Dozens of tanks would have their engines running inside the enclosed tank deck, warming up before the beach assault. Diesel and gasoline fumes had to be evacuated, or the crews would suffocate. The LST incorporated large blowers capable of exchanging the tank deck atmosphere completely every few minutes. In April 1942, To resolve remaining questions about ventilation, the Army constructed a full-scale mock-up of an LST well deck at Fort Knox, Kentucky. The building was constructed to duplicate every feature found within an actual LST, with the same dimensions and layout. Fort Knox, home to the Armored Force Board, supplied tanks that ran their engines inside the mock-up, while naval architects adjusted blower capacity and duct placement. The testing was completed in 3 months. The historic building still stands at Fort Knox today. An elevator was initially planned to transfer vehicles between the main deck and tank deck. This proved cumbersome during trials, and later models replaced the elevator with a hinged ramp, allowing vehicles to drive directly between decks without complex machinery. The crew would number approximately 113 officers and men. Additional capacity existed for several hundred troops, though comfort was minimal. LSTs were working vessels, not troopships. Hot bunks, where one man slept while another was on watch, were common. Food was basic. Privacy was non-existent. By January 1942, the first scale model had been built and was undergoing tests at the David Taylor Model Basin in Washington. Engineers towed the model through the test tank, measuring resistance, observing wave patterns, checking stability. The flat bottom created unusual hydrodynamics compared to conventional hulls. But the model behaved predictably. It would work. On February 6, 1942, Congress passed the first of 3 acts authorizing construction of LSTs, along with other amphibious vessels, destroyer escorts, and assorted landing craft. The authorization was remarkable. The Navy was committing to mass production of a vessel that existed only as drawings and a scale model. No prototype had been built. No full-size ship had been tested. The first LST crews would learn how the ships handled by taking them to war. The priority assigned to LST construction was extraordinary even by wartime standards. At Newport News Shipbuilding in Virginia, workers had already laid the keel for an aircraft carrier. The partially constructed carrier keel was hastily removed from the building dock to make room for LSTs. Several LSTs could be built in the same dock space as one carrier, and the landing ships were needed more urgently. The keel of the first LST was laid down on June 10, 1942 at Newport News. LST-1 was designated the class leader, though dozens of other LSTs were already under construction at shipyards across the country. The first standardized LSTs were floated out of their building docks in October 1942. 23 were commissioned by the end of the year. The LST building program was unique in naval history. Construction began before testing was complete. Contracts were let in massive numbers before the first ship proved seaworthy. The risk was enormous. If fundamental design flaws emerged, hundreds of ships would require modifications or might prove unusable. But the risk was accepted because the alternative was worse. The invasion of Europe couldn't wait for methodical testing protocols. The Pacific Island campaigns were already beginning. American factories could produce tanks faster than the Navy could ship them to combat zones. LSTs were the bottleneck, and that bottleneck had to be eliminated immediately. The construction effort spread across America. Shipyards on both coasts built LSTs, but the most remarkable achievement occurred inland, along the Ohio and Mississippi River systems. Shipyards in Pittsburgh, Evansville, Indiana, and other river ports thousands of miles from the ocean converted their facilities to build ocean-going vessels. The Evansville shipyard became the world's champion LST builder. Workers in that Indiana city, many of whom had never seen the ocean, built LSTs in assembly line fashion. The ships were constructed in sections, welded together, launched into the Ohio River, and sailed down to the Mississippi, then out through the Gulf of Mexico to the sea. By 1943, construction time for an LST had been reduced to 4 months from keel laying to commissioning. By 1945, that time was cut to 2 months. The production achievement rivaled the famous Liberty ship program. Between 1942 and 1945, American shipyards launched over 1,050 LSTs. 113 were transferred to Great Britain under Lend-Lease. 4 went to Greece. 116 LST hulls were converted to other vessel types, becoming repair ships, hospital ships, and various support craft. But the majority became what Niedermair had envisioned: beaching vessels capable of crossing oceans and landing armored forces directly onto hostile shores. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The first LSTs had to prove themselves before the skeptics would accept Niedermair's radical design, and there were many skeptics. Senior Navy officers who had spent careers at sea looked at the LSTs and saw ungainly boxes that violated every principle of naval architecture. The flat bottoms, the blunt bows, the minimal freeboard, everything about LSTs screamed unseaworthy. The early LST crews shared those doubts. The ships rolled in beam seas with a motion that induced seasickness in the hardest veterans. The flat bottoms slammed against waves, creating jarring impacts that rang through the hull like hammer blows on steel drums. The slow speed meant LSTs wallowed in swells that destroyers cut through cleanly. LST crews developed grim humor about their vessels. Large slow target was the most common interpretation of the LST acronym. Some crews claimed it meant large stationary target. Others said last ship to Tokyo, acknowledging that LSTs would always be the slowest vessels in any convoy. When an LST broached on a beach, unable to retract, the joke was large stranded target. But humor masked respect. Despite everything, LSTs worked. The proof came in early 1943 at Quonset, Rhode Island. John Niedermair, the designer who had created the LST in November 1941, travelled to Quonset to observe beaching tests. He needed to verify that his concept would work under real conditions, with real ships on real beaches. The commanding officer of the test LST was understandably nervous. The articles for the government of the United States Navy contained 18th-century language that was unambiguous. He who doth suffer his ships to founder on rocks and shoals shall be punished. Running a ship onto a beach at full speed seemed like an excellent way to founder on shoals, Niedermair insisted. The LST had been designed to beach at speed. The flat bottom and reinforced bow could handle the impact. The ballast system would adjust trim. The anchor and winch system would pull the ship off the beach when the mission was complete, but theory required testing. The test LST approached the Rhode Island beach at 10 knots, engines at full power, bow aimed directly at the sand. Officers and crew braced for impact. Niedermair watched calmly from the bridge. At the last moment before grounding, he leaned toward the captain and spoke quietly. "Don't reduce speed. Drive her on." The bow struck the beach with a shuddering impact that rattled through the hull. The LST drove up onto the sand, the flat bottom sliding forward, momentum carrying the ship 30 feet up the beach before friction and gravity overcame inertia. The bow doors swung open, the ramp dropped. A clear path existed from the tank deck directly onto dry sand. The LST sat upright, perfectly stable, even as waves broke against its sides. The flat bottom meant the ship wouldn't roll. It would sit exactly as it had grounded until the crew decided to retract it. Retracting proved equally simple. The stern anchor, a heavy Danforth design, was dropped and the winch engaged. The LST's own machinery pulled it backwards off the beach. The ballast tanks were then flooded, increasing draft, and the ship backed into deeper water under its own power. The test had taken minutes. Niedermair's concept was validated. LSTs could beach at speed, remain stable during unloading, and extract themselves without assistance. The design worked. What the Quonset test couldn't show was how LSTs would perform in combat. That answer would come in the Solomon Islands in June 1943, when LSTs made their combat debut delivering troops and supplies to Guadalcanal and nearby islands. The Japanese attacked with aircraft, submarines, and surface ships. LSTs proved harder to sink than anyone expected. The flat bottom that naval officers had criticized actually enhanced survivability. Torpedoes striking the bottom tended to explode at the junction of bottom plate and side plate, creating damage that was serious but rarely catastrophic. The massive ballast tanks, which had been designed to adjust draft, also served as excellent torpedo protection. A torpedo hitting a ballast tank would flood that tank, but the adjacent tanks remained intact, preserving buoyancy. The slow speed that made LSTs laughing stocks in convoy proved advantageous under air attack. Japanese pilots had trained against fast-moving warships. LSTs, plodding along at 9 knots, created aiming problems. Bombs released at predicted intercept points would miss because the LST hadn't moved as far as expected. The minimal superstructure and low freeboard made LSTs difficult to hit with horizontal bombing. Most of the ship's mass was below the waterline. Aircraft had to score direct hits on the tank deck or engine rooms to inflict serious damage. Near misses that would cripple conventional ships often did minimal damage to LSTs. Most importantly, LSTs proved extraordinarily difficult to sink. The compartmentalization built into the design meant that flooding in one section could be isolated. The huge ballast capacity meant LSTs could take on thousands of tons of water and remain afloat by expelling ballast elsewhere. The flat bottom and wide beam provided stability that kept damaged LSTs upright when conventional ships would have capsized. Throughout World War II, more than 1,050 LSTs were built. They participated in every major amphibious operation in both theatres. They landed troops in Sicily, Italy, southern France, and Normandy in Europe. They conducted hundreds of operations across the Pacific, from the Solomons to the Philippines to Iwo Jima and Okinawa. The statistics of LST survival tell the story Niedermair's design made possible. Despite being valuable targets carrying tons of fuel, ammunition, and vehicles, only 26 LSTs were lost in action during the entire war. Of those 26, only 13 were actually sunk by enemy fire. The rest were lost to accidents, groundings, and weather. 13 LSTs sunk by enemy action out of over 1,000 built, a loss rate of barely 1%. For comparison, the US Navy lost 22% of its submarines to enemy action. Aircraft carrier losses were lower, about 8%, but carriers operated with heavy escorts and avoided direct exposure to shore batteries. LSTs had no such luxury. They drove directly onto defended beaches, often under fire from artillery and machine guns. They operated in waters mined by the enemy. They anchored offshore in positions vulnerable to air attack and submarine torpedoes. Yet they survived. Part of that survival came from tactics. LSTs typically beached at dawn, unloaded within hours, and retracted before enemy forces could concentrate fire. Speed of operation mattered more than armor. Get in, unload, get out. Part came from the inherent toughness of the design, the flat bottom, the ballast system, the compartmentalization. Everything Niedermair had built into the concept to make LSTs capable of beaching also made them difficult to sink. But the real victory was strategic. LSTs changed what was possible in amphibious warfare. Before LSTs existed, amphibious operations required ports. The attacking force had to capture a functioning harbour quickly, or the offensive would bog down from lack of supply. Defenders knew this. They fortified ports. They prepared demolitions to destroy dock facilities if capture seemed inevitable. LSTs made ports optional. An entire armoured division could be landed on any beach with a gentle slope. Supplies could flow directly from ships to shore without cranes or piers. The attacking force could choose landing sites based on tactical advantage rather than proximity to harbours. This flexibility transformed Allied strategy. In the Pacific, General Douglas MacArthur used LSTs to conduct island-hopping campaigns that bypassed Japanese strongholds. Rather than assault every fortified island, MacArthur landed on lightly defended beaches, established airfields, and moved on. The isolated Japanese garrisons withered without resupply. Admiral Chester Nimitz employed similar tactics in the Central Pacific. At Tarawa, Iwo Jima, and Okinawa, LSTs landed Marines and their equipment directly onto reefs and beaches. The operations were costly, but they succeeded because logistics were solved. Tanks rolled off LSTs within hours of the initial assault. Supply dumps were established on the beach the first day. The attacking forces never lacked ammunition or fuel. In Europe, LSTs proved equally valuable. Operation Husky, the invasion of Sicily on July 10, 1943, was the combat debut for LSTs in the Mediterranean. More than 150,000 troops went ashore along 105 miles of coastline, landing on 26 different beaches. The invasion surprised Axis defenders, despite being one of the largest amphibious operations in history. The Germans and Italians had expected landings near ports where all heavy equipment could be unloaded. Instead, Allied tanks came ashore on beaches the defenders had considered secondary threats. Sicily fell in 38 days at a cost of approximately 24,850 Allied casualties. The Italian campaign that followed in September 1943 relied heavily on LSTs. Salerno, Anzio, and dozens of smaller operations used LSTs to land troops and supplies. The fighting in Italy was grinding and difficult, but logistics were never the limiting factor. LSTs could deliver Sherman tanks to any beach where the fighting required them. Operation Overlord, the invasion of Normandy on June 6, 1944, represented the ultimate test of amphibious warfare. The operation involved over 7,000 ships and landing craft, more than 195,000 naval personnel, and 133,000 troops landing on D-Day. LSTs were essential to the plan. The 5 landing beaches, Utah, Omaha, Gold, Juneau, and Sword, all received LST support. The ships beached repeatedly over the following days, ferrying tanks, vehicles, ammunition, and supplies. By June 30th, more than 850,000 men, 148,000 vehicles, and 570,000 tons of supplies had landed on Normandy's shores. LSTs handled much of that cargo. The importance of LSTs was demonstrated dramatically when storms destroyed the Mulberry Artificial Harbour at Omaha Beach on June 19, 1944. The Mulberries had been designed as portable harbours, towed across the channel to provide protected anchorage and cargo handling capacity. Losing one seemed catastrophic, but the invasion continued without pause. LSTs simply beached more frequently, offloading directly onto the sand. The tactical flexibility that Niedermair's design provided meant the Allies could adapt to circumstances that would have halted conventional logistics. LST hospital ships, 38 vessels converted specifically for medical duties, brought 41,035 wounded men back across the English Channel from Normandy beaches in June 1944. The ships that had delivered tanks and vehicles returned carrying the casualties of war. The flat decks that had held Shermans now held rows of stretchers. The crews that had unloaded ammunition now tended wounded soldiers. In the Pacific, LSTs were equally critical to every operation. The Battle of Leyte Gulf in October 1944, which destroyed Japanese naval power, was preceded by LST landings that put General MacArthur's forces ashore in the Philippines. The LSTs arrived under air cover, beached under occasional fire, and departed before Japanese forces could respond effectively. Iwo Jima, from February to March 1945, cost more than 26,000 American casualties, but was essential for providing an emergency landing field for B-29 bombers hitting Japan. LSTs landed Marines and their equipment under direct observation from Japanese defenders entrenched in the volcanic rock. The fighting was savage, but the LSTs kept coming, delivering replacement troops, ammunition, and supplies, even as Japanese artillery targeted the beaches. Okinawa, from April through June 1945, was the costliest battle in the Pacific. More than 12,000 Americans were killed and 36,000 wounded. Japanese losses exceeded 107,000 killed. Okinawan civilians suffered over 140,000 deaths. The battle demonstrated the fanatical resistance the Allies would face in any invasion of the Japanese home islands. LSTs made Okinawa possible. They endured kamikaze attacks that sank 30 ships and damaged 368 others. They continued operations despite losses, because stopping meant stranding the troops ashore without supplies. The crews developed tactics for surviving kamikaze attacks, positioning anti-aircraft guns to create overlapping fields of fire, maneuvering when aircraft approached, accepting that some attacks would succeed but ensuring most would fail. The final statistics of World War II validated every decision Niedermair had made in November 1941. 1,052 LSTs were constructed. 13 were lost to enemy action. 13 more were lost to accidents and weather. 1,026 survived the war. Compare that to other ship types. Destroyers lost 22% of their numbers. Cruisers lost 13%. Even submarines, which could hide beneath the waves, lost 22%. But LSTs, which drove onto defended beaches under fire, lost barely 1% to enemy action. The survival rate wasn't luck, it was engineering. Everything about the LST design contributed to survivability. The ballast system that allowed draft adjustment also provided redundant buoyancy. A torpedo could flood ballast tanks, but adjacent tanks could be pumped out to compensate. The flat bottom that naval traditionalists had criticized provided stability that kept damaged ships upright. The minimal superstructure offered few targets for aerial bombing. Most importantly, the compartmentalization that spread throughout the design meant that localized damage remained localized. Flooding in one compartment didn't doom the ship because watertight doors and bulkheads contained the water. Fire in one section could be isolated by closing hatches. The ship's survival didn't depend on a single critical system remaining functional. This robustness extended beyond combat damage. LSTs survived tropical typhoons that sank destroyers. They withstood groundings on coral reefs that would have torn the bottoms out of conventional ships. They operated in Arctic waters off the Aleutian Islands and in the heat of the Southwest Pacific. The design proved adaptable to conditions Niedermair couldn't have anticipated. The versatility of the LST exceeded original expectations. Ships designed to land tanks became platforms for dozens of different missions. LST repair ships serviced smaller landing craft, hauling damaged vessels aboard using cranes and booms installed for the purpose. LST hospital ships, with the bow doors sealed and medical facilities installed throughout the tank deck, evacuated casualties from beachheads. Some LSTs became rocket ships, with batteries of rockets mounted on the deck to provide saturation fire support before amphibious landings. Others became aircraft transports, though they never carried their own aircraft operationally. LST motherships, with additional berthing and supplies, supported flotillas of smaller vessels. Ammunition LSTs carried nothing but ordnance, resupplying beach dumps from offshore. The flexibility came from the basic design, a large, flat deck that could accommodate almost anything, bow doors that simplified loading and unloading, engines and machinery that were simple and reliable, crews that learned to improvise. LSTs became whatever the Navy needed them to be because the design imposed few constraints. After the war, hundreds of LSTs were scrapped or sunk as targets. The massive wartime construction program had produced far more ships than peacetime needs required. Some were sold to foreign navies. Many went to merchant service, their military equipment stripped out, their flat decks converted to cargo holds. A surprising number served until the 1980s or even 90s, a testament to the soundness of the basic design. But the real legacy wasn't the ships themselves. The legacy was what LSTs made possible. Amphibious warfare had been transformed from a risky gamble requiring perfect conditions into a reliable method for projecting power ashore. Modern military forces take for granted that troops can be landed anywhere with adequate beach gradient. That assumption rests on innovations pioneered by the LST. The LST concept influenced every subsequent amphibious ship design. Modern landing platform docks, landing helicopter docks, and specialized vehicles like landing craft air cushion all trace their lineage to Niedermair's sketch. The requirements haven't changed. Forces still need to move heavy equipment from ship to shore without port facilities. The solutions have grown more sophisticated, with helicopters and hovercraft supplementing traditional beaching vessels, but the fundamental problem remains the same as it was in 1941. John Niedermair never achieved fame for his contribution. His name doesn't appear in popular histories of World War II. No warships were named after him. No monuments commemorate his achievement. The historical record provides few details about his personal life, his motivations, or his thoughts about the ships that bore his design into combat. But the impact of his work is measurable in ways that transcend personal recognition. Every successful amphibious operation of World War II depended on LSTs. Every island liberated in the Pacific, every beach secured in Europe, every tank that rolled ashore without waiting for a port to be captured, all made possible because Niedermair solved an impossible problem in November 1941. The mathematics are straightforward. 1,052 LSTs were built. Each carried roughly 20 tanks or equivalent cargo. Over the course of the war, LSTs conducted thousands of missions, some ships making dozens of voyages. The total tonnage delivered directly onto hostile beaches exceeded anything previously accomplished in military history. But the real calculation is subtraction. How many operations would have failed without LSTs? How many battles would have been lost because tanks couldn't be landed quickly enough? How many troops would have died waiting for ports to be captured and repaired? The counterfactual is unknowable, but the direction is clear. Without LSTs, Allied victory would have taken longer and cost more lives. The solution to the impossible problem was elegant in hindsight. Don't design a ship that is both deep draft and shallow draft. Design a ship that can change draft. Integrate a massive ballast system into the hull structure. Use the physics of buoyancy to accomplish what hull form alone cannot. Accept compromises in speed and seaworthiness to gain capability that no other vessel possesses. Naval architects had the tools to design LSTs decades before Niedermair drew his sketch. The mathematics of ballast systems were well understood. The engineering required no new technologies. What was missing was the conceptual leap, the willingness to challenge assumptions about what ships should be. Niedermair made that leap because he had to. The British needed tank landing ships. The war demanded solutions, not excuses. Conventional thinking said the requirements were contradictory. Niedermair asked what would happen if you made the contradictions temporary rather than permanent, if draft wasn't a fixed characteristic but a variable condition. That question, and the answer it produced, changed naval warfare forever. The sailors who served aboard LSTs understood their vessel's importance, even when others dismissed the ungainly ships as targets. They endured the uncomfortable rides, the Spartan accommodations, the jokes about large, slow targets. They kept the engines running, the ballast pumps working, the bow doors operational. They beached their ships under fire, unloaded cargo while artillery rounds bracketed the beach, and extracted back to sea to bring another load. LST crews were rarely celebrated. Their ships lacked the glamour of aircraft carriers or the mystique of submarines. But they knew what they accomplished. Every tank that drove off their ramps and advanced inland was proof. Every supply dump established on a beach that had been empty hours before was validation. They were the bridge between ship and shore, and everything the army accomplished and on land began with LSTs making that connection possible. The veterans of World War II, who served in amphibious operations, whether as LST crew members or as soldiers and marines riding to beaches aboard LSTs, shared a common understanding. They had participated in the largest and most successful amphibious campaigns in military history. The scale of operations, from Sicily to Normandy to Okinawa, would never be matched, and all of it depended on ships designed by a naval architect whose name most of them never knew. John Niedermair wasn't at Normandy or Iwo Jima. He didn't storm beaches or pilot landing craft under fire. He sat at a drafting table in Washington and solved an impossible problem. His contribution was theoretical, mathematical, invisible to the men who fought. But those men survived and succeeded because Niedermair's theories were sound, because the mathematics worked, because the ballast system functioned as designed, because 1,052 ships built to his specifications proved nearly impossible to sink and capable of doing exactly what they had been designed to do. Engineering excellence, applied to military necessity, created a weapon system that shifted the balance of the war, not through firepower or speed or armor, but through the simple ability to put tanks on beaches. The LST was never glamorous, it was never fast, it was never beautiful, but it worked. And in war, that matters more than anything else. One LST survives today as a museum ship. USS LST-325, built at Philadelphia in 1942, served in the Mediterranean and later in the Pacific. After the war, she was transferred to Greece, where she served as Syros L-144 until 1999. A group of American LST veterans purchased her, restored her to approximate wartime configuration, and brought her back to Evansville, Indiana, where she now serves as a memorial. Walking through LST-325 today, visitors can see exactly what Niedermair designed: the enormous tank deck, extending the length of the ship, the bow doors, massive hinged plates that swing open to reveal the ramp, the ballast control stations, where crew members operated the valves that flooded or emptied the tanks, the cramped crew quarters, the Spartan galley, the simple but functional design throughout. The ship is smaller than visitors expect. 328 feet seems vast on paper, but feels intimate when you walk the deck. The realization comes quickly. This modest vessel, and 1,051 others like it, transported armies across oceans and delivered them directly onto enemy shores. The engineering is visible everywhere. The flat bottom, obvious when viewing the ship from the dock. The twin propellers, positioned high to avoid grounding damage. The reinforced bow, built to drive onto beaches at full speed. Every feature serves a purpose. Nothing is decorative. Everything contributes to the mission. Standing on the tank deck of LST-325, looking forward through the bow doors toward daylight, you can imagine what crews experienced. The approach to a hostile beach at dawn, the enemy coast growing larger, the sound of artillery fire ahead, the knowledge that within minutes the bow would strike sand and the doors would open, and whatever happened next would depend on speed and training and luck. And you can appreciate what Niedermair accomplished. He created a ship that crews trusted despite its ungainly appearance. He solved the impossible problem of deep ocean stability and shallow beach access. He designed a vessel that survived conditions that should have destroyed it. The ballast system, Niedermair's key innovation, is invisible to museum visitors. The tanks are below the deck plates, integrated into the hull structure, but the effects of that system defined everything LSTs accomplished. Without the ballast capacity to adjust draft, LSTs would have been unable to beach directly. Without direct beaching, Allied armies would have required captured ports. Without captured ports coming quickly, the war would have lasted longer. One innovation, conceived in November 1941, changed everything that followed. The story of the LST is ultimately about solving problems that seem impossible until someone solves them, about challenging assumptions that everyone accepts until someone challenges them, about understanding that constraints can be modified if you identify which constraints are actually variables in disguise. Niedermair looked at the requirement for ships that were both deep draft and shallow draft and recognized that both didn't need to be simultaneous. Sequential worked just as well. The ship could be deep draft in the Atlantic and shallow draft near the beach if it could change between states. That insight, obvious in hindsight but revolutionary when proposed, unlocked everything else. The design followed inevitably from that central concept: flat bottom for stable grounding, ballast capacity integrated throughout the hull, bow doors and ramp for vehicle deployment. All the pieces fit together once the central problem was solved. Innovation often works that way. The breakthrough isn't inventing new technology. It's recognizing that existing technology can be combined in ways no one has attempted. Niedermair didn't invent ballast systems. He didn't invent bow doors or flat bottoms or diesel engines. He invented the specific combination that made LSTs possible. The combination mattered because it solved a problem that had constrained military operations for centuries. Amphibious assault had always been limited by the need for ports. Attackers had to capture harbors intact or wait while temporary facilities were constructed. Defenders exploited this requirement, fortifying ports and preparing demolitions. LSTs broke that constraint. Ports became convenient but not essential. Armies could be landed anywhere geography permitted. The tactical options multiplied. The strategic flexibility transformed warfare, and all of it came from one engineer sitting at a drafting table, solving a problem that others had dismissed as impossible. The lesson extends beyond naval architecture and World War II. When faced with apparently contradictory requirements, the answer may be to question which requirements are actually fixed. What seems impossible might be possible if approached differently. What appears to be a permanent contradiction might resolve if examined from a new angle. Niedermair demonstrated that breakthrough thinking doesn't require genius, just willingness to challenge assumptions. The ballast system solution was elegant but not complex. Any competent naval architect in 1941 could have designed it, if they had thought to try. Niedermair thought to try because the problem required solving and conventional approaches had failed. That willingness to attempt the unconventional, to propose solutions that violated design norms, to accept that ugly and ungainly might work better than beautiful and traditional, that willingness changed the course of the war. 1,052 LSTs carried Allied armies to victory. 13 were lost to enemy action. The rest survived because Niedermair's design was robust, because the engineering was sound, because the concept worked exactly as intended. The men who served aboard those ships, the crews who maintained the engines and operated the ballast systems and drove the vessels onto hostile beaches, they fought the war at sea level, in the grind of daily operations, where theory met reality. They proved that Niedermair's impossible design was actually practical. The soldiers and marines who rode LSTs to combat, who drove tanks down the ramps onto foreign soil, who fought to expand beachheads that LSTs supplied, they never knew the name of the man who designed their transport, but his contribution enabled their missions. Innovation in warfare, like an innovation in any field, ultimately serves human purposes. LSTs weren't created for their own sake. They were tools to accomplish military objectives, but those objectives mattered because they determined whether democracy or tyranny would shape the post-war world. In that context, Niedermair's contribution to Allied victory was as important as any general's strategy or any soldier's courage. Without LSTs, the strategy couldn't be executed. Without the ships that could beach on open shores and deliver armies intact, the courage of individual soldiers would have been insufficient. All elements were necessary. None was sufficient alone. But the LST was the enabling technology, the innovation that made everything else possible. John Niedermair solved an impossible problem in November 1941. The British Admiralty approved his sketch immediately. The US Navy built more than 1,000 ships to his design. Those ships transported Allied armies to victory in both theatres of World War II. The recognition Niedermair received was professional but limited. His colleagues in the Bureau of Ships knew his achievement. Naval architects studying his designs understood his innovation. But public fame eluded him, as it does most engineers whose work enables great events without putting them in the spotlight. That's fitting, perhaps. Niedermair didn't design LSTs for glory. He designed them because the problem needed solving, and he had the skills to solve it. Allied ships worked. The missions succeeded. Allied forces landed on beaches worldwide, delivered by vessels that turned the impossible into routine. That success, quiet and unglamorous and absolutely essential, was Niedermair's legacy. 1,052 LSTs, 13 lost to enemy action, thousands of missions accomplished, millions of tons of cargo delivered directly onto hostile shores, victories made possible by ships that shouldn't have worked but did. The LST changed amphibious warfare forever. The concept Niedermair pioneered, ships that could cross oceans and beach themselves to deliver heavy equipment, became standard in navies worldwide. Modern amphibious vessels incorporate better technology, faster engines, more sophisticated systems, but they serve the same purpose Niedermair identified in 1941: put military force ashore where it's needed, without requiring ports, without delay, without limitation. That requirement hasn't changed in 80 years. The solution Niedermair provided remains valid today. Walking the decks of LST 325 in Evansville, Indiana, that connection to history becomes tangible. This ship, built in 1942, participated in history's greatest amphibious campaigns. She survived because she was built to Niedermair's design. She's preserved because veterans recognized her importance. The ship is a reminder that engineering matters, that solving problems elegantly can change outcomes as decisively as fighting battles courageously. That innovation isn't always dramatic or visible, but can be profound in its impact. John Niedermair drew a sketch in November 1941. That sketch became 1,052 ships. Those ships made victory possible. The impossible problem was solved. And somewhere, in the history that followed, in the beaches secured and the wars won and the peace achieved, Niedermair's contribution endures. Not in monuments or medals or public recognition, but in the fact that when it mattered most, when the future of the world hung in balance, his design worked. The LST carried armies to victory, and John Niedermair's ballast system, the illegal innovation that violated conventional naval architecture, made the LST possible. That is engineering's ultimate validation, not praise or recognition, but simply this: it worked when it had to work. And because it worked, history changed. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.